All right, here we are again, and it's a nice Thursday morning, and we got plenty of math to do today, but we also have a couple of new cool videos, which we'll be seeing in a while, and they will, of course, help us understand how math ties together with the real world. Anyway, so here's what we're going to do. First things first, we're done with chapters 5A and B, and so here's what I'd like to do. If you look at Moodle, you'll see, oops, no, that's not it. Oh, I know it's here. Oh, here it is. Oh, for God's sake. Here it is. So this is Moodle. Let me just go to our class. And you'll see in this section here with all the slides and all, there are 3 problem sets that I posted. There's one for actually each section. In other words, this one is for 5A, 5B, 5C. So before we get too far into the material, what I would like to do is on Monday, go over the problems from from this number 1 and number 2, because these cover chapters 5A and B. And so I just want to make sure that everybody's on the same page, that we all understand what we've been doing. So these are not meant to be collected. Don't send them to me. What you should do is work on them. And then when we go over them on Monday, you'll understand pretty quickly if you're getting the material or not. All right. So Monday we'll go over these in class, and hopefully you'll have been able to do them all. If not, this is the time to find out what went wrong. And this way you'll be ready when the test finally does roll around. Not for a while, I would say, probably not to the end of this month at least. But in the meantime, this way we can keep up with the work. And then eventually when we're done with 5C, then we'll do the 3rd problem set as well. But this Monday, just 1 and 2. All right, now in the meantime, we can go back and start 5C, which we didn't quite get to last time. And so we're going to start with some very basic properties of the real numbers that you may or may not be familiar with. And then when that's done, we're going to dive into some other topics. And like I said before, at some point, we'll watch these 2 videos, which again, will give you some more appreciation of how important numbers actually are in our daily lives. All right. So anyway, now the real numbers, of course, we already know the real numbers consist of all the rational and irrational numbers. And in fact, if we wanted to, we could write this out in terms of sets. You'll recall that this fancy R is the way we describe the real numbers. And it consists of 2 sets, the rational numbers. And we've seen this before, by the way, with a Venn diagram. So the set of rational numbers is combined with the set of irrational numbers to give us the real numbers. So this is set notation, which we will see again. And basically what it's saying is that we have 2 sets of numbers. One has all the rational numbers, one has the irrationals. This symbol is a shortcut or shorthand for the word union, which means that we simply combine the 2 sets into one big new set, which is the real numbers. Now, I do want to remind you that these 2 sets do not have any elements in common, but when we combine these, the resulting set is what we mean by the real numbers. Now, we also know that the rational numbers contain other subsets like the integers and the whole numbers and all the rest. But for here, all I wanted you to see is that the rational numbers are composed of 2 sets, rational and irrational numbers. All the numbers have to be one or the other, but none of them can be both. All right, now, there's some key properties here that we need to be aware of. Now, many of these you've already seen before. You are aware of them, and you use them on a regular basis, but you may not have realized that they have a name for them. So let's look at these really quickly. There's 6 of them. We'll start with these 3, the so-called closure property. Now, these next 2 you should have seen somewhere along the way, the commutative property and the associative property. They should sound very familiar because you definitely have seen these before. It's probably been a while, but you've definitely seen these. And when we start doing these, you'll probably start to remember them very, very quickly. So they have these 3, which are the second and third, at least, you should be very familiar with. And then there are 3 more, of which one I'm sure you've seen before. All right, so let's take a look at the next 3. Okay, Hold on a second. The next three are the identity property and the inverse property, which, by the way, these showed up in the video we looked at the other day about why we can't divide by 0. Well, we'll see how in a few minutes. And then finally, the one that should be very familiar to you, the distributive property. As soon as you see it again, you're going to say, oh, there's no way I could have forgotten that. And so even if you've seen it, though, before, and you may still have started to forget how it works, or you may have forgotten that it has this special name. So what we're going to do is start with the simplest one, the closure property. All right, here we go. Closure. Now, this is defined for addition and multiplication, and really it's a very simple idea. If we take any two real numbers and add them together, the sum is also real. In other words, it's not possible to create an imaginary number simply by adding together two real numbers. Now, it might seem kind of silly and obvious, but this is an important detail. It means that we cannot, or we can guarantee that anytime we add real numbers together, the resulting number is also real. Now, you'll discover as we go along that mathematicians do everything in terms of proofs. In other words, it's not enough to say, well, most of the time this is true, or a lot of the time this is true. For mathematicians, things have to either be true all the time or never true. We don't normally have sort of or semi cases. It's either all or nothing. And so they spend a lot of time proving that certain statements are true or they are not true. And so this is one of those cases we can prove without a shadow of a doubt that anytime we add two numbers together, the resulting number is also real. And so we refer to this as the closure property. You notice how it's not called a theory, because we know and we can prove that it's true for all real numbers. And that's the key detail. There are no exceptions. For all real numbers, if we add them together, we wind up with another real. Now, the same thing holds for multiplication. So there's two separate properties here. There's a closure property for addition, and there's one for multiplication. And of course, this is kind of common sense. If I multiply two real numbers, it's not possible for that result to be imaginary. So I end up with AB, which is guaranteed to be a real number. All right, so this is something you might not have seen before. It's one of those properties that's going on behind the scenes, but you may not have been explicitly told what the name is. Now, having said that, the next property, I'm sure you've seen this one before. It's called the commutative property. Whoops. So basically what this is telling us is that the order in which I add two real numbers is irrelevant. In other words, if I have two numbers A and B, A plus B equals B plus A. Now, like I said, intuitively, everybody knows this, but you might have forgotten that this actually has a special name, this property. It's called the commutative property. And you can see we're applying it for addition. And I've got a couple of examples here. And by the way, this also applies to negatives. In other words, all real numbers, literally every single one of them has this property. So for example, what about these two? 3 plus 4 equals 4 plus 3. Okay. Negative 2 plus 7 equals 5, but so does 7 plus negative 2. So therefore, you can see, and it turns out that we can prove that no matter what two real numbers we're looking at, this will always be true. And of course, you can prove it to yourself. You can punch these into your calculator and you'll always get the same results. But this is formally known as the commutative property of addition. Well, now, do you think this applies to multiplication? And the answer is yes, of course. So let's see how. If I take two real numbers A and B, A times B equals B times A. Of course it does. So let's see some simple examples of this. 3 times 4 equals 4 times 3. Of course it does. Negative 2 times 7 equals 7 times negative 2. Now, interestingly enough, though, this does not apply to either subtraction or division. Okay, let me just remind you that there's a big difference between 2 minus 3 and 3 minus 2. And the same thing is true with division. 2 divided by 3 is not the same as 3 over 2. But 2 plus 3 equals 3 plus 2. And 2 times 3 equals 3 times 2. So the commutative property only applies to addition and multiplication. And of course, you learned this so long ago that it's become like second nature. You know this. You just might have forgotten that this property is called the commutative property. Now, around the same time you learned about the commutative property, you probably were also exposed to the next one, which is called, and if you dig through your memories, you'll say, oh, I remember this one too. It's called the associative property. Now, this one's a little different because this tells us what happens when we apply parentheses to sums. And you can see what it's essentially telling us is that the placement of the parentheses does not affect the results when the only thing we're doing is adding, right? Parentheses do affect our results if we have different operations mixed together here, especially ones that are at different levels of precedence, like especially multiplication and addition. But because all we're doing here is adding, the fact that the parentheses are here in the left-hand side and over here on the right-hand side does not affect the results. Either way, we just simply end up with A plus B plus C. And again, this is something you've seen, but you may have forgotten about. This idea is known as the associative property, specifically the associative property of addition. Very good. So let's look at a few simple examples. And you can see in all of these cases, the placement of the parentheses has no effect on the final result. And again, because we're applying them to all operations, all the same operation, in other words, all addition. We don't have a mixture, for example, of addition and multiplication or addition and exponents. It's all addition. So therefore, the parentheses are not only affecting our results, not affecting the results, we don't even need them. Okay, in other words, these parentheses don't really contribute anything to this equation, do they? They're not really necessary. I mean, you can put them in there if you want to, but you just don't need them. Very good. Now, does this also apply to multiplication? Well, I think you know the answer to that. The answer is, of course it does. If I apply parentheses to only multiplication, the order or the placement of the parentheses does not affect the results. So in other words, this is saying that, for example, 2 times 3 times 4 equals 2 times 3 times 4. How do you know? Because if you evaluate what's going on in these parentheses, you'll see that that's in fact the case. They're both the same, aren't they? Oh, yes, they are. Okay. All right. And again, you can see why, because we only have multiplication in this equation, which means that the parentheses do not change anything. Remember, the purpose of parentheses is to change the order of operations. That's not going to happen here. All right, let's look at a few other simple examples. You notice even when there's negatives involved, these rules still work. The placement of the parentheses does not affect these outcomes. And this, again, is known as the associative property of multiplication. All right. Now, the next property, you may not have heard of this before, or maybe you have. We'll see. Boy, it turned out to be very important. This next batch of properties turned out to be very important when we watched that video, which explained in great detail why we can't divide by 0. All right, that proved to be important, as you remember. All right, the so-called identity property, there's an identity property for addition, which simply tells us that if we add 0 to any number, we still have the original number. Okay, adding 0 to something doesn't do anything. And so therefore, 0 is often referred to as the identity element for addition. Okay, identity means it's the same. It's like if you, I can't think of an analogy in the real world. I don't know. I guess if you just change your clothes, for example, you're still the same person. Your clothes are irrelevant to your identity. That's the best I can do at a moment's notice. But adding 0 numerically doesn't change the value of A. That 0 is a pretty tricky little number, isn't it? And of course, we've already seen, I guess, okay, there you go. I like that one, looking in a mirror. Your identity hasn't changed, has it? No. But yes, we've already seen from 2 very cool videos that 0 is such an important number in the real number system. In fact, the lack of a 0 is one of the reasons why we don't still have Roman numerals, among other things. There was other problems with it too, but the lack of a 0 proved to be a real problem. The Romans, for whatever reason, resisted the use of 0. I guess it didn't make any sense to them, and so their numbering system disappeared. While, of course, we're still using their alphabet to this very day. So that survived, just not their numbering system. Well, now, if there's an identity element for addition, isn't there one for multiplication? Yes. And so obviously we all know that if you multiply a number by 1, you do not change its value. So we say that 1 is the identity element for multiplication. And this helps us out a lot. Like, for example, what if I want to combine 2 fractions? Oh my God, what do I do now? I know. Let's find a common denominator. What am I doing? I'm going to multiply each of these terms, or one of these terms, by 4/4. Actually, no, sorry. This one gets multiplied by 3/3. I'm not changing anything. This is 1 and this is 1. And yet, look how convenient this is. I now have 8/12 plus 9/12, and I can easily combine them to come up with, 17/12. Yeah, that's better. You've all done this before, but this was always based on the principle that these are just ones. You can multiply any number by not only 1, but any ratio that gives you 1. Okay, so that's why this is just a simple example of when this property can be very, very helpful. So we call one the identity element for multiplication. And then we move into the inverse property, which is closely related to the identity elements. So we know, for example, that if I take any A and add its negative, I end up with 0, which is the identity element, which means that this negative A has its own special name. It's called the additive inverse of A. So for example, 3, let's put it this way, -3, for example, is the additive inverse of +3, because their sum gives me back the identity element of 0. All right, so whatever A is, its negative or opposite number, as you know, we defined that earlier in the course, its opposite added together give us 0, which means that they must be additive inverses. Now, the next type of inverse is the one you're probably more familiar with. It's the so-called multiplicative inverse, and this is the one that trips up division by 0, if you recall. All right, so let's move on to this one. If I have any number, real number a, and I multiply it by 1 over a, I end up with 1, which is, of course, the identity element for multiplication, which means that 1 over a is the multiplicative inverse of a. So, for example, 1/3 is the multiplicative inverse of 3, because their product is 1. And so they made the case in the video that dividing by 3 is really just the same thing as multiplying by the multiplicative inverse of 3. So there's the rub with 0. For if a is 0, 1 over a does not exist because there is no number x such that 0 times x equals 1. Okay, so in other words, the fact that we cannot find a value whose product with 0 is 1 indicates that there's no multiplicative inverse, which implies in turn that we cannot divide by 0. This is the thrust of their argument, by the way. We can't find a multiplicative inverse for 0, therefore it's not possible to divide by 0. End of story. Now, it's not the only way to prove it, but I'm hoping that it was the most straightforward way of explaining why by 0 is disallowed. Very tricky concept to wrap your mind around. A lot of math can get very, very deep in a real hurry, as you know. You know, it's more than just multiplying numbers together. I mean, math itself is a very deep and intense area of study. All right, now the final property that we want to look at is another one that you've seen before, possibly you've forgotten the name. It's called the distributive property, specifically we call it multiplication over addition. Why? Because what it's saying is that if you have this expression, you can rewrite it as a times b plus a times c. So the multiplication, we say, is being distributed over the addition. So if you do this in terms of an algebraic expression, for example, this is going to give you 3x. Oops, what happened there? 3 times x plus 3 times y. Now, you intuitively know this. You may have simply forgotten that it has a special name. The distributive property of multiplication over addition. This is the one you see all the time. Beautiful. So let me just show you a few simple examples with constants. And by the way, in each of these cases, as is so often the case with math, there's multiple ways of evaluating an equation like this. I can just simply consolidate these two if I want to, and I end up with 2 times 7. But if I apply the distributive property, I'm going to end up with 2 times 3 plus 2 times 4. Actually, let me draw this like this. 2 times 3 and 2 times 4 are added, and guess what? I get the same thing. Now, how about this one? Even though there's a negative, it still applies. So here I can start by just saying, well, all right, this is just 10. So I end up with negative 30, but I can also use the distributive property to show that this is minus 12, minus 18, which is, of course, the same thing. Okay. Now, we're going to move into a new topic here, which is something that you're very, very familiar with. And what would that be? That would be our old friend exponents. And we also have another old friend coming to visit, which is scientific notation. Now, this is something you learned about in science class. Yes, like chemistry. Do you remember those days with fondness and physics, the hard mathematical sciences? Yes, no, don't be like that. You loved chemistry and physics, didn't you? That's right. I bet some of that knowledge is still stuck in your memory. Yes, like for example, what is the charge of an electron? Ooh, it's negative. That's right. You see, it's still stuck in your memory, whether you like it or not. How about this? What's the atomic weight of oxygen? 8. It's one of the so-called noble gases. Remember all this good stuff, the periodic table of the elements? Oh my God, all those, yeah. Didn't you? You took great pride in memorizing the names of all those elements, didn't you? And some of them were very bizarre. Like, for example, gold, believe it or not, the atomic symbol for gold was AU. The atomic symbol for silver was AG. How does this happen? Well, because these came from foreign languages. Um, lead was PB, for God's sakes. Potassium is K. That's right. It's coming back in a flood. And some of them were very straightforward, like N is nitrogen and O is oxygen. But there's some wacky ones in there too. And so I don't know. I just thought that was a lot of fun, the table. But there were certain ones like xenon, krypton, some of the other bizarre ones. They were all collectively known as the noble gases. Remember that? Oh, yes. Those were the days. Oh, argon. I forgot about our old friend argon. Those are the 3 of the noble gases. And they have certain cool properties. Oh, those were the days. Yes, they were. But what the point of all this, when you see this discussion, is that many of the numbers we used in these sciences are either huge or they're tiny. For example, the speed of light is an enormous number. The weight of an electron is a tiny, tiny little number. And so it's often more convenient to express them in scientific notation than use all the zeros. So when we get back to this, it'll start to come back to you. But in the meantime, we're going to review exponents. Now, first things first, what exactly is an exponent in the first place? If I take a, some constant, and multiply it by itself n times, all of this can be simplified as a to the nth power. So for example, 3 times 3 times 3 times 3 is 3 to the 4th because I've got 3 multiplied by itself 4 times. That's what it actually means. It's just a shorthand way of expressing the idea that you've multiplied 3 by itself 4 times. Beautiful. Now, there's a few key details that we need to remember. What did I write here? This is not physical, it's physics. Chemistry and physics, that's right. Everybody has to take science to get out of high school in New York State, but it doesn't have to be chemistry and physics. But if you did stumble into those, you'll know that, yes, scientific notation is heavily used in those disciplines because we often encounter either enormously large numbers or tiny little numbers. All right, but as far as exponents are concerned, there's something you may not be aware of, but when you write out an exponent like this A is referred to as the base of the expression. Of course, n is the exponent. And if, let's say that it's multiplied by some constant, then this constant is referred to as the coefficient of the expression. So like, let's say, for example, you have 3x to the 7th power, then you have coefficient of 3, you have a base of x, and you have an exponent of 7. And when we start looking at algebraic properties of exponents, it's important to be aware of these terms. Beautiful. All right, now let's look at some special results. For example, first we got some other examples here. Just as a quick reminder what exponents actually mean. And also, whenever we have a new example, this might be a golden opportunity for you to get some practice with your calculators. For example, here, your calculator does have an and when I say calculator, I mean either you've got the iPhone or else you have another calculator which you are very familiar with. And the results might be slightly different if you do not have the iPhone. So for example, here on this calculator, there happens to be an X cubed button, which makes things a lot easier because all you have to do is hit that button, 2x cubed, and you're done. So why don't you try it, 2x cubed, and there's your 8, okay? But for this next one, we don't have an x to the 4th power. We have x to the y power, but then you have to tell the calculator what your exponent is, and that gives you that one extra step. You also need an equal sign. $81. And now here we also have a button already built in, and that means we just go 5x squared, no equal sign, you're done. Now, some calculators do not have an x cubed button, but they all have to have a button which gives you any exponent you need, and it will either be, typically it's either x to the y, y to the x, or sometimes you might have this thing. On the high-end Texas Instruments, they have this symbol, if you've never looked at your keyboard before, is directly above the 6. This has a special name, this symbol. It's called a caret, believe it or not. Not to be confused with this kind of caret. What kind of caret is that? It's usually used to represent the purity of a diamond. Okay, so this caret is not that caret, and it's certainly not this caret. Okay, no, do not confuse these. Which, by the way, that reminds me, here's a fun scientific fact for you. The word caret, now this is apropos of nothing, but I just want you to know because it's kind of fun. Whenever an opportunity arises to learn something fun and new, I think we should grab it. The reason why those vegetables are called carrots, because they contain huge amounts of a substance, and I'm not sure of the spelling. I'll have to double check this. This is something that's good for you, by the way. I think it's carotene. I have to double check that. No, oh, okay. There's a couple of ways of spelling it apparently. Keratin. Oh my God, I didn't get it, did I? Well, anyway, you get the point. It's a very short journey from keratin to carrot. So that's what that's all about. So in fact, um, well, anyway, so all right, let's get back to this. So beta carotene is what makes it orange, and it's very useful to human beings. In fact, supposedly it helps with your vision, but it eventually came out of that, or at least the roots that mean beta carotene. All right, anyway, so enough of that fun stuff. So now, as far as the special case goes, um, any number raised to the zero power is defined to be equal to one. Okay, so no matter what it is, zero exponent means you have one. Very interesting. How about this one? If I raise a number to the first power, all I end up with is the original number. That's it. So for example, 3 to the first power is just 3. X to the first power is just x. So when you see an x, it implicitly has an exponent of 1. It isn't often written there, but it is there. It is x is actually x to the first power. Negative. Now, this is something I've noticed over the years, that a lot of people are confused about what a negative exponent actually means. It has nothing to do with negative numbers. It's just a notation that means what you're actually doing is you're taking the inverse of the positive value. In other words, a to the minus n is defined to mean 1 over a to the positive n. So, for example, 3 to the minus fourth equals 1 over 3 to the positive 4. Okay, so in other words, that's what it means. It's 1 over that base raised to the positive exponent. So I have some simple examples on it. And by the way, this is another golden opportunity to practice with our calculators. It's important to be able to use negative exponents as well as positive exponents, but every calculator is different. So you have to keep an eye on that. All right, so are we ready? Yes. So 3 to the minus 2 is 1 over 3 squared, which is 1 over 9. And so in this calculator, you would type 3 exponent. Now, remember on this calculator, the way it expresses negatives is to have the number itself followed by this button. And then you'll need an equal sign. 3, x to the y, 2 negative equals. Now, if you do it this way, you're going to come up with 0.11111111, which you might recall is simply 1 to the 9th. Now, if you want it to show this, watch what you can do. There's a button on the far left-hand side, 1 over x. If you hit that now, it's going to give you 9. And what it's telling you is that 0.11111 is 1/9. So this button is basically saying, take the inverse of. And by the way, specifically the multiplicative of x. That's why it's there, in case you need it. Now we'll do the same thing here. To execute this on your calculator, you would put 5 x to the y, 3 negative equals, now this time, we're going to see that that equals, on your calculator, when you go through all those steps, it'll turn into 0.008. And you might say, well, what is that the equivalent of? Once again, if you hit the 1 over x button, you'll get 125. So that is it's telling you that 0.008 equals 1 over 125. So we did a couple of very important things here. We used the negative button. And by the way, most calculators do use this approach, but if you're using one of the expensive Texas Instruments calculators, they have a separate button for the negative. It's on the bottom next to the period. And so if you wanted to type in -3, for example, on the Texas Instruments 84, you would put this button followed by the 3. So that one is very different. The high-end calculators tend to be a little different than what we're doing here. All right, but they all have this 1 over x button, which is, again, our multiplicative inverse. Excellent. Man, they're getting very complicated, aren't these examples? Well, is there anything left that we can do? Yes. You know what's missing? The fractional exponents. And they can get a little tricky. All right, so let's carry on now. Let's look at some fractional exponents. The first couple are easy. For example, I mentioned earlier that, or last week or whatever it was, that the square root of x is nothing but x raised to the 1/2 power. So, well, there it is. So for any real number, if I raise it to the 1/2 power, this symbol is the same thing as saying raise this value to the 1/2 power. On your iPhone calculator, the button for that actually contains the 2. When you see the symbol without a number in here, it's understood you're talking about a square root. This calculator chooses to put it there explicitly. All the rest of them do have to have a number. So on your calculator, don't be surprised to see that the square root button has a little 2 here, because that's what this thing really means. So for example, if I wanted to know the square root of 9, what you could do is just hit 9 and then hit the square root button. And well, wait a minute, hold on. 9. Yeah, you don't even need the equal sign. It'll show up with the 3. If you choose to go this way, here's what you have to do. 9 exponent, open parentheses, 1 divided by 2, close parentheses, equals 9 raised to the parentheses, 1 divided by 2, close parentheses, don't forget about that, equals, and you'll get your 3. Now, you probably wonder, why should I go through all these steps down here when I have this wonderful square root button? Well, the answer is, unless you're dealing with square roots or cube roots, or squares or cubes, all the rest of the cases you might encounter require you to go through all these extra steps. So therefore, you might as well get some practice. All right. It's nice to have a shortcut once in a while, but you really need to know how to do it properly. In other words, use the most general case. Okay, now, what about this one? 1/3. 1/3 means cube root. And you see now we have to put the 3 here. because these both mean the same thing. So for example, what if you went to your calculator and said, I want to know the cube root of 8? You could do this, and your calculator does have a cube root button. And if you do that, you're going to get a 2. No problem. If you want to do it with this expression, you'd have to type 8 x to the y, 1 divided by 3, close parentheses, and equal. Again, it's a lot of extra steps, but in general, this is what you're going to need to do for any fractional exponent you might run into. You can use the shortcut keys if you want to, but you should also know how to use the other these steps to get any other results you might need. And of course, don't forget, the reason why this is true is because 2 cubed is 8. So the cube and the cube root are essentially inverses of each other. So, it's just like if you said 5 squared is 25, therefore it must be the case that the square root of 25 is 5. Very good. Now we're going to see a very strange case. You're going to say, what's going on here? These two we're already familiar with, but what about this one? Two-thirds, what's going on with 2/3? Okay, now here's a way you can understand what this really means. I'm going to write this in a very interesting way. I'm going to rewrite it as a to the 2 times 1/3 power, which I'm certainly allowed to do. But what this helps me recognize is that what I'm really being asked to do is take a squared and apply the cube root to it. So in other words, it's fine to remember this, but if you understand it, you won't run into any problems. Now, having said that, on your calculator, suppose you needed to know, let's say, 64 to the 2/3 power. You would write 64, and you see how this is exactly like what we were doing before. Okay, and so 64 to the 2/3 power. Now, I just made that up. I hope it turns out nicely. Oh, it did not. Wait a minute. Hold on. Did I screw this thing up? I wanted to pick a nice one. I may have goofed it up. Oh, no, it's 16. Oh, I'm relieved. I wanted it to turn out as a nice number. So yes, go ahead.
I just said it did. Yay.
Is it working?
No, yeah, it's a nice one.
Oh, okay, good. Yeah, I was afraid it was going to be like 5 radical 13 or some nonsense. No, it's 16. Perfect. Because we prefer nice numbers to ugly numbers, don't we? Yes. 16 is a nice number. So anyway, but 2/3, yes, 64 to the 2/3. And in other words, what we just did was we took 64 squared, raised that to the 3rd power, and 64 squared is 4,096. And so the cube root of that, as you'll see if you go to your calculator, is in fact 16, because 16 times 16 times 16 is in fact 4096. So don't be shocked when you see these fractional exponents. I got a few others here. These are pretty straightforward. Like now, this is obviously just the square root, which is 3. This is the cube root, which is 8. I'll tell you what, let's just for the fun of it, I'm going to make one up right now on the spot and see if we can. Let's see. I'm going to try to make one up that turns out nicely, and then we're going to do it together. Oh, this one worked out beautifully. All right, let's try this one. No, wait, hold on. Here we go. Not 16, 32. Let's apply this 32 to the 4/5 power. And based on what I told you before, this is actually the 5th root of 32 to the 4th power. All right, so let's see what you can come up with. 32 raised to the 4/5 power. Anyone have a number?
It's 16.
It is 16, yes. Now, if you wanted to do this step by step, and you did it in your calculator as 32, x to the y, 4 divided by 5 equals, and you ended up with your 16. But what you could have done, if you felt so inclined, is to evaluate 32 to the 4th power. And, like I said, there's always many ways of doing these math problems, but look how big this number is. Oh my God. And then what you would have done is said, all right, calculator, 1,048,576 raised to x to the y, sorry. X to the y, 1 divided by 5. And you would have gotten the same result. But I think you'll see that it's easier to just do it directly like this. All right, nice. Now, this is all great, but what happens if we need to apply algebraic operations to these exponents? It turns out there's some nice rules that we can apply that simplify things for us. All right, so when you see these rules, you might recognize them, you might not, but that's okay. We're going to see how they work. And so we'll see that there's 3 of them. We have the product rule, the quotient rule, and the power rule. The power rule refers to what amounts to an exponent of an exponent. Okay, the others are pretty self-explanatory. All right, so let's see how these guys work. All right, let's begin with the product rule. And suppose I have 2 numbers. Now, before we go any further, I just want to mention that none of this works unless both of these have the same base, okay? If they don't, then these rules are not going to work. We have a to the m, a to the n, we multiply them, and wow, look how easy this is. I add the exponents. So for example, 3 to the 2nd power times 3 to the 4th power equals 3 to the 6th power. Now you can prove this by first writing these out. And this gives you 729. And then if you go to your calculator and say, okay, calculator, tell me what is 3 to the 6th power? It'll turn out, wait a minute, what did I do? $729. I don't know. There's something about this calculator. I tend to make a lot of typos on it. That's because I'm used to the physical calculators like the Texas Instruments. The buttons are a little bit bigger and they're physical buttons. You can feel them. So with this thing, you've got to keep your eyes open all the time. On the other hand, I didn't grow up using cell phones, did I? No. So that's why it's a bit of a disadvantage for me to use this thing. All right, so let's take a look at some more examples. 83 graph. Oh, is that an Apple app? Graph. Oh, this is good. Anytime anyone has any useful information for me about potentially useful products, I'm up for it. Graph calc. Let's see. Look at this thing. What is it doing? Graph and Calc 83. Oh my God. Is this an app for the TI-83? Ooh, that would be a nice thing to have. But, because it's a very advanced calculator, you might not need it for this class. Wow, look at that. I had no idea this even existed. Well, thank you very much. I'm very happy to see that this is here. Because, yeah, look at that. Ooh, look at all those cool functions it has. Man, is this free? Oh my God. Oh, it's amazing. How do these apps make money if they're free? Does anyone know? If I'm making it, what is it?
Ads.
Where would you see ads on an app? Like if I'm using their calculator app, when would I ever see ads? Oh, I don't know. All right. Well, whatever. I mean, I'm sure they know what they're doing. I'm not going to ask questions. I'm like, why are you giving this to me for free? Instead, I'm saying thank you. It's amazing what people are willing to give away. I mean, like I said, with YouTube, there's so much good stuff on YouTube, and you're not paying for it. You're free to share the knowledge of all these other people. Well, like, okay, well, we're the consumer. Yes. And this is what by one thing I have noticed though is that if I later on, if I were to go to look at even a website like ESPN.com, how much do you want to bet there's going to be an ad there for this app? Yes, they know. They know me too well. They follow me everywhere with the ads. Yeah. They're gonna say, oh, so you're interested in graphing applications. Ooh, look what we have for you. It happens all the time. In fact, just one day I was looking at an ad. There's a website for this company that sells historical coins. I was actually using it for a finance class, but then I noticed that for quite a while, every time I went to a website, they had ads for all these historical coins. I was thinking, huh, they know their stuff. they know what I want, and they're going to keep telling me that they have it until I buy it. I guess after I actually buy it, then they'll really flood me with ads. But in a way, I don't mind because it helps me find things that I do want that I didn't know about, like this one. So I'm okay with it. A lot of people are not, but I am okay with this because all they're doing is trying to sell me products that I want anyway. They're actually doing my research for me, aren't they? Kind of. All right. Well, anyway, so let's look at some examples of the product rule. And again, in all these cases, I've done it in two separate ways. So you can see that they're equal to each other. Here down here, I've obeyed the rules. And I got 2 to the 5th, which is 32. But here I evaluated each term separately before multiplying them. And of course, I have to get the same result. Down here, same thing. You've got the sum of these two. And again, you notice the important detail is that they always have the same base. If I had 2 to the 3rd and 4 to the 5th, there's nothing I can do here. Or at least I can't use the rule. I can simplify them, but I can't use the rule, the product rule. So here I've got 3 to the 6th. Oh, just by coincidence, this is the same example I made up before. It is equal to 729 any way you look at it. Anyway, now if there's a product rule, there has to be a quotient rule. Of course. What does that look like? Oh, there's more. Sorry, there's more. I put these in here because they involve special cases. We have negative exponents and we have zeros, but you can see nothing changes. We're still adding the exponents. But up here, of course, I don't have to do that. I've chosen to evaluate each one separately, and I still end up with 4. Down here, the 0, of course, means that the exponent is just 2, which is 4 squared or 16. Down here, we recognize that 4 to the 0 power is 1. This is 16, and so the product has to be 16. All right, so now we should be ready for the quotient rule. And let's take a look at it. So here, what's different is that we're dividing, and so instead of adding the 2 exponents, we subtract. The only thing we have to watch out for is that, of course, a cannot be 0 in this case. Otherwise, we'll end up with division by 0. All right. So let's look at some examples. Here, for example, now again, I'll do it 2 ways. I'll evaluate each term separately before dividing. And I get 4 here, but look how easy this is. 5 minus 3 is 2, and that also gives me 4. Now, if you want to do this on your calculator, it's not a problem. Watch how easy this is. 2 raised to the 5th. Now, here, you do need the equal sign. And then what you're going to do is divide by 2 raised to the 3rd. Now, that seems like a lot of steps, doesn't it? All right, let's confirm this real fast. 2 raised to the 5th equals, don't forget that equals, divided by 2 raised to the 3rd. Oh, hold on a second. 2 raised to 32 divided by 2 raised to the 3rd. And I end up with 4. Yeah, that's it. So I think in this case, you're probably better off with just 2 raised to the 2nd. Yeah, yes, it should be 4. Perfect. But by using the rule, look how much simpler this is. How nice that is compared to this. So maybe there's a reason why we should use this rule. If all it does is speed things up a little, that's enough reason to me to use the rule. Also, if these 2 numbers are unusually messy, you're probably better off with this, because then you can start introducing rounding problems. Okay, what about these 2? Oh, well, no, it's actually just 1, but what's different now is that the numerator is smaller than the denominator. So like down here, when I apply the rule, I end up with 2 to 3 to the negative 1 power, which is actually, as you know from before, 1/3. In fact, if you go to your calculator and type 3 to the minus 1, 3 raised to the, don't forget, you need that plus minus thing. 3, 1, and don't forget this minus thing. It'll give you 3, 3, 3, 3, 3. And if you want to confirm that this is 1/3, you can hit the 1 over x button and it will give you a 3. All right. Let's see. Are there any other? No. Okay. Now, the third and most complicated case is the so-called power rule. Now, this is important. It's different than what we've done so far. If you look at this very carefully, you'll see that this is not the same as this. What's happening here is I'm taking a to the m power and then raising the entire expression to the n power. It would be like having this. This actually means 3 cubed multiplied by itself twice, which equals 3 to the 3 plus 3 power, which is 3 to the 6. Whereas over here on this side of the fence, 3 cubed times 3 squared is very different, isn't it? This is where I would add them up, and I get 3 to the 5th. And if you're not sure, you can prove it by recognizing that this is 27, this is 9, and the product of 27 and 9 is, hold on a second, 243, which is also 3 to the 5th. But over here, I've actually got, this is 27, this is 27. I'm actually multiplying 27 by itself and to come up with 729, which is also equal to 3 to the 6th. All right. So with all that being said, just remember the rule. But here's the thing. It's easy to get confused between the power rule and the product rule. That's why I went through all of this. Very good. All right. So let's see some examples. And again, you can always choose to evaluate it directly. Here I'm using the rule. 3 times 2 is 6, which gives me 64. But here I've evaluated 2 cubed as 8. Then I squared it. And I still have the same result, of course. Down here, I multiplied these to come up with my 8. Or the alternative is to turn this into 81 to the 2nd power. And of course, it's the same number. It has to be. Okay. Now, all right, as soon as we're ready. Now, we're ready for scientific notation. Now, because this is a completely new topic, in my opinion, this is the perfect time to stop for a minute and watch these insanely cool videos that I've come up with. Now, the first one is going to show you a very interesting look at infinity and how there can be different levels of infinity. And it also brings back our old friend prime numbers along the way. So this is a more conceptual video. The second video is more about how numbers pop up in the real world. So we're going to start with the first one because it's kind of mind-blowing. We want to have our minds blown first before we relax and look at some applications. I think you'll agree when you see these that this is the way to go. So let me go get the links. First, I'll stop sharing. I'll send you the links. And then we're going to watch some amazing videos, let me tell you. So, whoops, hold on. I do not, oh, here we go. This one is called the Infinite Hotel Paradox. All right, here we go. Now I know it's a little close to lunchtime to have your minds blown, but you know what? You can deal with it. All right, here we go. Be prepared to be amazed. In the 1920s, the German mathematician a hotel with an infinite number of rooms and a Wow, that was pretty impressive, huh? You'll be thinking about that for a long time. Oh my God. Don't worry, the next video is not very conceptual, but it may be very surprising. They're basically what they've done is patched together a bunch of very amusing facts about math and how it shows up in the real world. Some of them are very interesting. Some of them are like, like it's a mixed bag. Let's put it that way. But I think you'll like it. It's there's something for everybody in this video that's coming up. All right. Are we all ready to watch the second video? All right. So, all right, I'm going to just post it up there. Good, good, good. And this one is a little longer. And so it may take us to the end of the class, but that's okay. I really want you to see this one. It's really good. A lot of fun stuff in there. In fact, so much you may want to go back and revisit it when we're done. Oh, here it is. Hold on. All right. So this one is called Interesting Facts About Numbers and Prime Numbers. Here we go. Let's take it away. All right, is everyone pretty much done? All right, so I guess we'll have to stop here because the next topic is something we don't want to rush into it. So don't forget, though, what I'd like to do on Monday, though, is go over the chapter 5, problem set number 1 and 2 before we get back to the new content. All right, so don't forget. And so then, other than that, unless there's any last minute questions, I'll just see you on Monday. All right. Okay, I hope you enjoyed that video.
Thank you.
Thank you.
You're welcome.
Thanks.
Okay,
Thank you.
you're
Bye.
welcome. Okay, bye.